It's an honor. Yeah. Okay, how's that? Maybe. All right, let's try again. So thanks for coming. It's great to be here. Yeah, I don't know if this will be as entertaining as the last lecture, but I'll do my best. Also I guess the first few lectures of this series are going to be pretty similar to ones I gave at TOSI and PITP. So sorry if you were there, but maybe hearing it again you'll understand it better. Okay, so the basic question I'm going to talk about is the emergence of bulk physics in AdS CFT. There are lecture notes for the first part, which are online on the archive. It's called TOSI Lectures on Emergence of the Bulk, so you can look at that if I'm going too fast. The basic kind of questions I want to understand, say starting in AdS CFT, is how do we think about physics deep in the bulk from the CFT point of view, and in particular, how can we think about the interiors of black holes? So that's kind of the problem that I want to solve. And so everything that I'm doing is aimed at trying to understand the black hole interior one way or the other. So this is a hard question, and we haven't solved it yet, but we've learned some things, and so I'm going to tell you about some of the things that we have learned, rather than complaining about the things that we haven't. So the topics I'm going to try to get to is so representing bulk operators in the dual CFT. Bulk in stuff that's in the gravity theory that's not right at the boundary. We're in the bulk. So then I'll talk about toy models of holography, which are exactly soluble. And so it's always good to have exactly soluble toy models. I will talk about the Ru-Takanagi formula and how I like to interpret it. I will talk about something which is called entanglement wedge reconstruction, where I'll explain more about what it is later. But basically it's something about, if you have access only to some subregion of the degrees of freedom in the CFT, what can you learn about in the bulk? So this is basically the answer to that question. And then finally, I'll use kind of the machinery that's been developed to argue that there are no global symmetries in the bulk. So that's an old conjecture about quantum gravity, but here we can argue for it fairly rigorously.
Both discrete and continuous?
Both discrete and continuous, yes. And so part of that, depending how much time we have in the last lecture, we'll spend some time agonizing over what exactly we mean by global symmetries, which is both in quantum field theory and quantum gravity, which of course is an important question in general. All of these results are going to come from interpreting the AdS CFT correspondence as a quantum error correcting code, which is something that I'll define when I get to it, but it's something that's come out of the theory of quantum computation. And my goal is just to give you some idea of how that connection works, and give you some sense of how results like these can follow from it. Okay, so that's the big plan. And this stuff is all in the lecture notes that are online. This will be based on a paper, really two papers I wrote with Hiroshi Aguri. There's a long one and a short one with a compression factor of 35 between the two. So probably you want to look at the short one. But the long one is very educational too. Actually, it's probably better for students in some sense, the long one, because we try to pedagogically explain everything. Okay, So that's it for the overview. So now let me start by just saying a few things about AdS CFT, which I guess, at least in the lectures I've been in here so far, I think no one has done it yet. Maybe Subir, I guess, had a little bit in some sense, but okay. So the basic idea of AdS CFT is that quantum gravity in asymptotically AdS spacetime is equal to CFT on r times SD minus 1. So we can draw a picture. So here's the bulk theory. So time is going up, and there's some angular direction here, omega, and then there's some radial direction here. And in the interior of the can, you have quantum gravity, and could be black holes. There could be people, whatever going on in here. And G Newton is greater than 0. And then this is supposed to be equal to or defined as having conformal field theory, just living on the boundary of the space-time. And so since this is conformal field theory without gravity, so there isn't any G Newton. So in this side of things, there is an SOD, 2 asymptotic symmetry group, which is basically the set of diffeomorphisms that preserve the boundary conditions but act non-trivially at the boundary. And then here there's a SOD, 2 conformal group. And then you can ask, what does this arrow really mean? Well, one way you can think about it is that there's a map from the Hilbert space of quantum gravity in AdS to the Hilbert space of the CFT, which is an isomorphism, and which has a nice relationship with this symmetry. So in particular, if you compose this with these SOD, 2 here in the bulk, then you get the CFT symmetry acting with the map in the other order. Okay, so maybe a mathematician calls that intertwiners. I don't know, but so the Hilbert spaces are mapped onto each other. So this is invertible, and in such a way that it preserves the symmetry. So in particular, the spectrum of the Hamiltonian is the same on both sides. For every state in one theory, you have a state in the other theory, and so on. And so it's really a quantum mechanical statement. And so to make
How does the symmetry act on the gravity theory? You said it was trivial on the bulk, right?
No, yeah. So what I said was it was the set of diffeomorphisms which preserve the boundary conditions but act non-trivially on the fields at the boundary.
On the boundary, right?
On the boundary. Yeah. So it's like So if you were in Minkowski space, it would be sort of diffeomorphisms that become Lorentz transformations at large distances. Here it's diffeomorphisms that become the isometries of AdS at long distances. They're not. You don't say that it's isometries of AdS everywhere because AdS is only one state. Most of the states don't have the symmetry, so most of the states transform in non-trivial representations of the symmetry group. It's just like U1 gauge symmetry in electromagnetism, right? There's some flux at infinity which generates the symmetry. And the states transform under it. What is phi and what is U? Well, so U is just the unitary group, the unitary representation of the symmetry on the Hilbert space. So here it's the asymptotic symmetry, and here it's the conformal symmetry. Phi is the map that defines the correspondence. So it tells you which bulk state corresponds to which boundary state, and which boundary state corresponds to which bulk state. Yeah, to some extent it's a little bit heuristic because we only really know how to define this side. So in some sense, we really define the bulk by phi inverse. If you want to be precise, probably that's the right way to interpret AdS CFT, is it's a definition. But then you ask, okay, but is it a definition that's consistent with our sort of perturbative understanding of what's going on in the bulk, right? And to the extent that it is, we say it's a good definition. I'll say a little bit more about that in a sec. Okay, so now, well, I'll say it now. So we're especially interested in those CFTs where this bulk theory is semi-classical. You know, I mean, you can say, if you want, you can say, oh, you know, I don't know, the Ising model is dual to quantum gravity in AdS, but it's kind of a useless quantum gravity in AdS. So, you know, when this is good is when this gravity is something like the gravity in our world, you know, maybe with the wrong sign of the cosmological constant. Those are going to be CFTs. So yeah, we like semi-classical examples, which are ones where there's some finite set of primary operators, OI, in the CFT. And then there is some bulk effective action, S of phi I and lambda, where these are going to be the fields in the bulk, and these are the operators that we're going to say are dual to them in the CFT. And moreover, this lambda has the property that we can think of it as being large in AdS units and small in Planck units. And then if we, on the bulk side, using this effective action, compute expectation values of some bulk objects I'll define in a sec, T1 lambda 1, On of omega 1, Tn omega n, then these are equal to the CFT expectation values of these primary operators. T1 omega 1 O n of Tn omega n in the CFT. And then the key equation, which I guess I'll put up here because I'm running out of space, is what are these bulk O things? And so the idea is that this OI of Ti omega I on the bulk side is defined as the limit as r goes to infinity of r to the delta times some bulk field. The bulk field's appearing in this path integral here, Ti omega I. Okay. And so this is sometimes called the extrapolate dictionary of AdS CFT. So it says that if you take a field in the bulk and somewhere here, and you extract it to, extrapolate it to a point on the boundary, then you get a primary operator in the CFT. So as a statement about CFTs, it's saying that the correlation functions have this alternative presentation as a bulk path integral with an effective action with a cutoff scale that's high in AdS units. Okay. And so those are all, and so I'm not, so it's a very interesting question, right? What CFTs have this property? You know, the Ising model, it doesn't have this property. Most CFTs probably don't have this property. It's not a question I'm going to discuss in these lectures. I do discuss it some in the lecture notes, so there are various conjectures about what properties the CFT needs to have. I'm just going to assume that any CFT I discuss has this property, that the correlation functions have this funny alternative presentation as a bulk path integral. Okay, let me also say that in this discussion, I'm ignoring the issue that sometimes what actually happens is that near the boundary, you don't just have AdS, you have AdS times something. So the canonical example is like AdS 5 times S5 is dual to n equals 4. So if you keep track of the S5, then some of this, like for example, this equation needs to be a little bit modified because you need to talk about what happens when you do the extrapolation, what happens on the 5 sphere. So I'm just going to ignore that. Again, there are some comments about that in the lecture notes. But for now, roughly speaking, the way you can think about it is that this cutoff scale is going to be high compared to the AdS scale, but low compared to whatever compactification scale you have in string theory. So that in the bulk, we just have AdS. Yeah.
When I say equal, is this perturbatively in H bar?
This equal is to all orders in G. Yeah, that's right. Yes. Yeah. Yeah, absolutely. So that's what this asymptotically AdS means. So that means that in this bulk path integral, you have boundary conditions, which the metric and all the other fields have to obey. And in the bulk, you can work out perturbatively what those need to be. Sorry, Sasha, do you have something you want me to explain?
No, it's my poor vision.
It's also my poor handwriting, so. Yeah.
I have a question. The dual CFT lives on R cross a sphere when you have the AdS in global path.
Yeah.
So I can sort of understand why you were interested in global path, but if
Yeah.
You have some other slicing of AdS, would it be easy to generalize what you have here?
Yeah, that's right. So in principle, yeah. So I get that's another one of the things I was not going to discuss in detail. But in principle, we should require this not just for this example, but we should require it sort of for any reasonable manifold that we put here. And in particular, probably we want to include Euclidean ones, because we kind of need to do that to make sure that the black holes work out right. And so, yeah, I'm happy to implicitly also do that, yes. Okay, so let me just make one other comment, and then I'll be done with AdS CFT 101. And maybe I'll just put the comment here, because then I can erase all the boards and start with something different. So this set of rules is good enough if the only kind of experiments you want to understand in the bulk are scattering experiments. So experiments where, you act with some operators in the CFT and send some stuff in, and it evolves in, and maybe something happens, and then you wait at the boundary and kind of see what comes out. So any experiment like that, this rule just reduces it to a CFT correlation function. And so since we're playing by the rules that we've got the CFT and we know all the correlation functions, that means we know the answer to any question like this in the bulk. Okay. Unfortunately, it's not so clear that every question in the bulk you could be interested in is a question like this. Let me give you an example of one that isn't. Maybe let me erase just so I can make it bigger. I guess this picture you don't need. So an example would be like, say you have the AdS Schwarzschild geometry. So it's one of the standard things that I won't review, that this is described by 2 copies of the CFT on the sphere in the thermofield double state. So one experiment we could do is we could send in a particle here, and we could send in a particle here, and then now the scattering happens up here, and we could ask what comes out of this scattering. Okay, but now the outcome of the scattering doesn't make it out to the boundary because it's behind the horizon of the black hole. So it reaches up into the singularity instead. So I don't know how to turn this into a question about CFT correlation functions. Now, there may still be some way of doing it, right? I mean, I'm not saying I have a theorem that you can't turn this into a question about CFT correlation functions. I mean, in some sense, everything in the CFT is a question about CFT correlation functions. But if I don't know how to do it, if I don't know which correlation functions, it's not very helpful. Okay.
Like one of these out-of-time autocorrelators?
No, I don't think so. Not in general, yeah. So sometimes you can try to turn these into out-of-time order correlators, but in general, I don't know how to do it. So like the canonical, I mean, this is just one example of something, but the question in general, and if I'm in some arbitrary high energy state and I jump in, right, even the question of do I see a firewall at the horizon or not is a question I don't know how to write down. That's not some out-of-time order correlation function, at least not involving a small number of operators. Yes?
Why don't you consider the boundary beyond the singularity? In string theory, we have black holes where you have boundary beyond singularity.
What you mean, like is it maximally extended Reisner-Nordstrom or something? Well, I don't believe in that. That's a figment of Einstein's imagination. That's not really there. Yeah.
About that region also.
Well, yeah, good, but I don't have a reason to say it about this region. Yeah, for that one, I do have a reason to say it. Yeah, that we think is unstable. We think that once you include quantum effects, there will be a space-like singularity, or at worst a null one, and you're not going to see beyond that. Yeah.
Is there some reason we have to restrict ourselves to the correlation functions in CFT? Like, could we just consider the Schrodinger equation in CFT?
Yeah, but the usual idea is that you don't lose anything by just talking about the correlation functions, because you can extract the entire Hilbert space and all the operators from those.
We need a ground state or something.
Well, yeah, these are correlation functions in the ground state. No, but to get the other states, I can just include the operators here that create that state as part of the correlation function.
But if you have no stationary state, then
sorry, what do you mean by no state? I mean, in CFT, I always have the vacuum. Yeah. Okay. All right. So then, kind of the goal is for the rest of the lecture series is to sort of start developing machinery that might help me understand answers to questions like this. Okay. Like what happens back? Like if I jump in here and you jump in there, you know, what happens up here? Yeah. Do I see you or not? For example, like there are papers where people say if I jump here and you jump there, we meet, and there are other papers which say if I jump here and you jump here, we don't meet, right? And well, that's just a yes or no question, right? Like there should be an answer. If we say this is a theory of quantum gravity, then we better know what's the answer to that question. What? Yeah, that's right. Right, exactly. So there are papers say that you die here and I die here. There are papers that say I go in here but I don't see you. There are papers that I say I go in here but I do see you. Right? I mean, it's kind of embarrassing, right? You know, we say we have this theory of quantum gravity, and even these kind of seemingly simple questions, we fight about it, right? Okay. All right. So that's just kind of the motivation. So right now we're going to try to solve that problem. And as I said in the beginning, we're not going to succeed, but we're going to learn something. I'll leave this here for now. Okay. So now let me talk about bulk reconstruction. Okay, so the meaning of this term bulk reconstruction is to come up with a representation of the CFT. So we gave a CFT representation of this thing where we take the limit of a bulk field to the boundary. Okay, the goal of bulk reconstruction is to come up with the CFT representation of phi of t, r, and omega without taking the limit. Okay. I don't know why it's called reconstruction. That's you have to ask, I don't know, Dan Kabat or somebody to explain that to you. But anyways, maybe it should be called bulk representation. I don't know, or yeah, whatever. Anyways, it's called bulk reconstruction. So now there are two obvious complaints that you can make as soon as I tell you that this is what I want to do. Okay, and probably you're all sitting here thinking the complaints already. So let's get them. I like to address them right at the beginning. Okay. So the first complaint is that phi of r and t and omega is not diff invariant. So in a theory of gravity, there's no such thing as local operators. Okay, just for the same reason that in a gauge theory, there's no such thing as local operators that are charged under the gauge symmetry. So that's true. And it's something that we have to deal with, okay. But so far at least it's been kind of a technical thing. So the standard way of dealing it is you just either you just pick a gauge, or you use something which is called dressing to define the operator in a diffeomorphism invariant way. So the canonical thing that people talk about is you just pick a point on the boundary, you shoot in a geodesic which is normal to the boundary, and then you put for some renormalized distance, and then you put the operator at the end of it. And so that's some gauge invariant definition of where the operator is. And this sort of gravitational Wilson line, which is attached to it, is something that doesn't show up at leading order in the G Newton expansion. But if you go to high enough order, then it shows up, and you have to be careful about it. And it matters that I started from this point and not from that point or whatever. So I mean, it's part of the definition of the operator. So from now on, I'm gonna sweep this issue under the rug, with reassuring you that if you're careful about it, it doesn't change things very much. But feel free to ask about it whenever you're worried about it. Okay, so that's complaint number one. Complaint number two is that we learned when we were in junior high school reading Hawking's book that S is equal to A over 4G. And then we learned, maybe in grad school or wherever, that this means that the bulk is not local in a sort of more profound sense, because what this says is that if you have some space-time region, and the number of degrees of freedom that are in the region scales like the surface area. And so that means that you can't really have a formulation of the theory in terms of a local action in the bulk that makes sense non-perturbatively, because if you did, then there would just be too many degrees of freedom. You would have a volume's worth of degrees of freedom in a region instead of an area's worth. And you can just, since we're doing AdS CFT anyways, you can just say, right, I mean, really the thing that's local is the CFT, right? So why should you expect something like this to make sense at all? Okay. Well, on the other hand, right, I mean, we do this all the time, right? We're doing it right now here in this room, and it seems like a pretty good approximation that we have this local action. But we do have to somehow deal with the fact that really the theory is holographic and the microscopic degrees of freedom don't at all look like what they look like in the bulk, at least from the point of view of effective field theory. And that is a real problem. That's not a technical problem. And so most of this lecture is going to be to understand kind of how, despite the fact that this is true and that all the degrees of freedom in the CFT, that somehow it's still able to pretend to be a local theory in the bulk, even though it isn't. Okay. Now, we'll begin with just, maybe that all sounded cryptic, but hopefully by the end of the lecture series, you'll have a better sense of kind of the interplay of this with the bulk local presentation. Okay, so I'm going to start a first attempt at doing bulk reconstruction is, okay, so let's call this the naive reconstruction. Just the obvious thing to try. And sometimes this is called HKLL, which stands for Hamilton, Cabot, Lifshitz, and Low. Lifshitz is Israeli. Is he here, actually? I don't know. Gilad, are you here? Okay, he's not here, but anyway, he's... By the way, also Bekenstein is Israeli. That's true. Yeah. Everybody knows that. Yeah. Okay, so the naive proposal is that we just solve the bulk equations of motion. So since this is our favorite equation up here, I'm going to try to use it throughout the talk, and I'll give it a name. This is equation star. So we're going to try to solve the bulk equations of motion using equation star as boundary conditions. Okay? So this is like the dumbest thing you could imagine, right? So this tells us what the boundary values, this is an operator equation that tells us what the boundary values of phi are on a sort of codimension 1 surface, which happens to be the boundary of space-time. And then, well, this action leads to local equations of motion in the bulk. And so we can just try to solve those PDEs as operator equations to get a formula in the CFT for this phi anywhere in the bulk. Okay. And so that's this HKLL procedure, although I think it was actually first done, so I should put this here also, by Banks, D, who is D? Douglas, yeah, it's Michael Douglas, and Gary Horowitz, and Emil Martinek. Yeah. So they sort of did this first in a sort of just very casual way, and then it was turned into a systematic thing by these people.
What exactly are you saying is not invariant under what is?
Well, say I have an operator here, and the operator is at r equals 0, t equals 0. Okay. That's clearly not a diffeomorphism invariant statement, because I can just do a diffeomorphism, of compact support just in this region that changes the location of that operator and does nothing out at the boundary. And so that we're supposed to view as a gauge symmetry. So nothing physical should care about whether or not we did that diffeomorphism.
So then when we say solve the bulk equations of motion, you need also some boundary condition in the interior. you need to assume some specific state, or how are you solving the equation?
No, you don't. So I'm gonna do it explicitly in a sec. But at least in principle, if I give you the boundary condition over here, you might say I have to assume regularity in the interior. But that's not a boundary condition, right? If it weren't regular, it wouldn't obey the equation at that
for a
point.
for a very specific state, right? I mean,
No,
the state
no.
would be not regular in the interior, right? You'd have some objects in it and so on.
No, but even if even if you have objects, it can still be regular, right? I mean.
Oh, but we know that many things are sources, whatever. You have some brain in the middle. I don't know.
Yeah, but that.
Whatever.
Well, yeah, but all that would have come in, right? It's. No, but I think that's the statement that it's an operator equation that I'm solving. So the expectation value of the operator kind of knows, right, what's there in the state. But the state is supposed to enter only via the state you compute the expectation value.
So you are going to put in also the boundary condition that the expectation value is the next subordinate term, right?
No, I'm not. I'm not going to use the expectation value at all. I'm just going to solve this operator equation. Let me do it, and then maybe you'll be happy. Okay. So for simplicity, I'll do it working in the Poincare patch, which is something I usually avoid like the plague, but it just makes the calculation here easier. So I'm gonna do it. And this is going to, by the way, we're going to solve the equation perturbatively. So first I'm going to do it for a free field in AdS. But then it's something I won't show you how to do the interactions explicitly. But then it's something you can iterate the interacting equations to include the interactions. And let me also say that although I'm doing it around the vacuum, if you include the equation, if you iterate the equations to all orders in perturbation theory, then that gives you something which you can resum and use the same thing in other states. Okay. So in the Poincare patch, right, I guess we have z equals infinity here at the Poincare horizon, and we have z equals 0 out here at the AdS boundary. So the metric So let's just think about what do we know about, say, a free scalar field in the Poincare patch? Well, the basic thing is that we can expand it in terms of modes, which are solutions of the AdS wave equation. So we do a Fourier transform in the x mu directions. And it's going to have support only when k squared is negative. And then there will be some kind of radial wave function depending on z and also on k squared. There will be the Fourier transform, and then there will be some creation and annihilation operators. Okay. And so here I'm including both the creation and annihilation operators because I'm allowing omega to be negative. And this psi is something which goes like some constant n times z to the delta as z goes to 0. And in general, it's some Bessel function. And this delta is determined in terms of the mass of the field by the usual formula relating the scaling dimension and the mass. Okay, so now the idea is, okay, so this is going to be true, and in this equation, the only thing that's an operator is this A. Okay. Now, the idea is that, okay, we can take this equation and we can just take z to 0, and then we can match onto this. Okay? It's an operator statement. And so if we do that, we learn that O of z and x is integral d dk over 2 pi d theta minus k squared nk e to the I kx ak. Okay, I just used the asymptotic form of the Bessel function. And this tells us, now we can hit this with the inverse Fourier transform, right? And it tells us that this ak is just nk inverse times the Fourier transform of the CFT operator here. Okay? Maybe one thing that's not clear. This r here is actually 1 over z, sorry, in the Poincare patch. Yeah. And actually, this is all we need. because OK, we know what it is. It's just the Fourier transform of a local operator in the CFT. That gives us this AK as an operator in the CFT in terms of things we know in the CFT. And then the rest of this is just C numbers. So we just stick this AK in here, we integrate it against these known functions, and we get an operator in the CFT. And then you can check that the algebra of this operator in CFTs that are holographic turns out to be the right algebra. And actually, you don't even need to use that it's holographic. You essentially just have to use conformal symmetry. OK. So let me just also write that equation in position space. So in position space, this says that phi of z and x is equal to some integral over the boundary, some function k of z and x, and also of x prime. Let me call it, sorry, integral over x prime, O of x prime, where this function is called the smearing function. And you can trace through the Fourier transforms to see what this k is some integral over k of some combination of this psi and n and e to the ikx, x minus x prime. So this is, again, pretty simple. Here's the bulk field wherever you want. It's just some non-local integral of O, the operator dual to phi. And the integral is over the whole boundary of the Poincare patch. And so in particular, I want to emphasize that this integral is non-local in time, right? It includes O at different times in the boundary. So let me emphasize that a little bit further. So we can unwrap the boundary of the Poincare patch. It just looks like this. So here I've just taken the CFT, and this is going once around the circle. And we have an integral which is over this whole diamond. It's an integral of a local operator over this whole diamond. So let me emphasize that you could also try to represent that in the CFT just using Heisenberg operators on this time slice by evolving the operators back. But when you do, you're going to get a very horrible non-local mess. Because in quantum field theory, if you take a local operator and you conjugate it by e to the minus iht, right, it grows into a non-local operator along the light cone. And so you can represent this here in some very complicated way, all at t equals 0. And when you do, you're using operators throughout the entire time slice of the boundary. OK. So that's one comment. I feel it. I feel you, man. Okay, so let me make two other comments. So one is that there's a bit of non-uniqueness in this representation of phi, because for one thing, I picked the Poincare patch, but there's nothing to stop me from having picked a different Poincare patch where I put the point where at x equals infinity, say here or here or here or something, right? And those would give me representations in the CFT which look different, but are actually representing the same thing from the bulk point of view. And in the bulk theory, they would also look different, but they would just be different Bogolubov transformations of the same operator, so they'd really be the same operator. Okay, so that's one comment. The other comment is, and this one, I said it before, but I want to say it again because it's important. So this procedure, I just did it for the free field, but you can do also in perturbation theory include interactions, including gravitational interactions. So that's very important because a lot of the there are lots of papers about this bulk reconstruction, and everybody has their favorite way of doing it, and in 80% of them, they do it using conformal symmetry. Okay, if you do it using conformal symmetry, that works for free fields in the vacuum, but it doesn't work in general. Okay, and the whole point of this is that you actually want to get something that includes the bulk interactions, and the only known way of doing that is this HKLL procedure of solving the equations perturbatively.
Something, but in the exercise which you have demonstrated,
Yeah.
the dynamical gravity didn't appear at all.
Yeah, that's right, because I didn't work to high enough order. But it's
free field, so.
yeah, that's right. But once I start including interactions, that'll include gravitational interactions. And so, yeah, so maybe I'll just say briefly the kind of thing you get when you include interactions. So what happens is you get corrections to this. So the first one involves a double integral over this region, okay? And then it'll involve two operators here. And then so that kind of thing will come, say, from a 3-point vertex. And one of those vertices will be phi, g mu nu. So then you'll get something over here which is like O times t in the CFT. And as you go to higher orders, all the operators are going to show up. You know, J, T, other O's, everything.
This is all at tree level, right? We're not doing loops.
Well, no, but you can also go to loops. Yeah. There's nothing to stop you from going to loops. Because the statement that the operator obeys its Heisenberg equation in the bulk is a statement that's correct quantum mechanically.
But your definition is just on the space of states that look like a small number of particles over the vacuum. Not give any definition.
Yeah. Absolutely, absolutely right. So the kind of states where this will work are states where you have ordered one numbers of quanta in the vacuum. Yeah, and then you can reproduce all the correlation functions and interference and interact everything, but in that restricted setting.
And
Yes.
then it looks, you take a T and try to evolve it into the bulk. In this simple example of free
Yeah.
fields, you just use linearized
That's correct.
equation and ignore all non-linear.
That's correct. So at leading order, I didn't do it because it had more indices, but I could have put g mu nu here, and then I would have gotten some formula where it was t mu nu appearing here. And in doing that, I would have had to pick a gauge, which relates to this comment that I made before. That's right. But at leading order, the metric is just some free spin 2 particle. Who cares, right? So yeah. But once you include interactions, then you see it's really gravity. Yeah. Yeah. Why did I put it there? Yeah, so that good. So you can ask, why did I put this here? So that has the question of what are the modes that show up when I discuss a free field in AdS, okay? So the rules are when you do free field theory in any background, the modes have to be what's called normalizable modes, which basically means that the definition is in terms of the Klein-Gordon inner product, but basically it means you want to get a closed Hamiltonian system. You don't want information to flow out at the boundary. And that restricts the kind of modes that can appear here. And one of the restrictions is that k squared has to be negative. So I just included that here by putting the theta. Yeah. Because this function has an analytic continuation to positive k squared, but don't use that. Yeah. Okay, any other questions? Okay. All right. So that's the kind of the sort of naive way of doing bulk reconstruction. Oh yeah, sorry. Let me make one other comment. So you could ask okay, so what? I mean, how did I know which equations of motion to use, right? Because if we just start from a CFT, right? I mean, I could actually do this for any old equations of motion. I could put in the wrong equations of motion, right? And I could still solve them. And this procedure would give me some formula in the CFT, right? What would go wrong? Well, what would go wrong is that the operators that you construct this way wouldn't have the right algebra in the bulk. So the canonical thing that could fail is that at space-like separation, they would fail to commute. So you can kind of try to run things either way. So you can say, if I don't already know the equations of motion, then I can try to figure them out by demanding that these O's have the right algebra of a local quantum field theory. I think a better algorithm is just start with the ones where everything is at the boundary to determine the S matrix and figure out the bulk effective action from that. Once you know the bulk effective action, then you know the equations of motion, and then just use those ones and don't use the wrong ones. And remember that bulk effective action had a cutoff, so it's an effective field theory, and when you do the loops, so that'll regulate the loops and so on. But all that I'm sweeping under the rug. Absolutely, yeah, it's absolutely effective. Yes, that's right. That's right. That's the best you're going to get. Yeah, I don't believe in loop quantum gravity. Okay. All right, so we saw already in the Poincare patch that there was some ambiguity in which Poincare patch we picked. Right, and in the bulk, that was some issue of doing Bogolubov transformations. So there's actually a more interesting version of that, which I want to talk about now, which I'll call subregion duality. Okay, so I picked the Poincare patch, but actually there's another patch that I could have picked, which is called the AdS Rindler patch. So let me just remind you, what is the AdS Rindler patch? So the idea is we have a t equals 0 slice of the bulk, and then we can cut it in half along the equator. And then in the bulk, there's some region here, and we can take its domain of dependence, which, if you like, is just the set of points that are completely causally determined by initial data on this slice. So there's a natural set of coordinates on this subregion of AdS where the metric looks like this. Okay, so this is the Euclidean hyperbolic plane in d-1 dimensions. Then these are kind of Schwarzschild or Rindler kind of coordinates. So tau equals infinity is up here. Tau equals minus infinity is down here. And then the horizon here is at rho equals 1. Yeah, maybe I guess I haven't been giving homework problems. I suppose one of them was figuring out that smearing function. But another one could be, figure out, say, given the global definition of AdS as a submanifold of 2 d minus 2D signature Minkowski space, and figure out how to get to these coordinates. Figure out, what is this subregion, and what are the coordinates that I need to pick in order to get the metric to look like this. And so this is called the AdS Rindler wedge. Okay. Now, the point is that we can do the whole thing that we just did in the Poincare patch. We can do it again in the AdS Rindler wedge. So we can expand a free field in terms of modes, which will be a function of rho and tau. And I'll call alpha, I'll call the location on the hyperbolic plane. So we can still do the Fourier transform in the tau direction. We can also do it on the hyperbolic plane, but now we have to use the hyperbolic spherical harmonics. And then there will be some radial wave function, psi omega lambda of rho, which again will go like some coefficient n omega lambda times rho to the minus delta at large rho. I didn't say, but the asymptotic boundary again is still rho equals infinity. So then we can do the same manipulations that we did before to come up with a formula where we say that phi in the interior of the wedge is going to be equal to an integral over the boundary of the wedge. Let's just say d capital X. So by that I mean both tau and alpha. And then there will be another one of these smearing functions. I'll call it k hat of little x and big X times O of big X. Okay. So any phi which is inside of this wedge, I can represent in the CFT just with support, just by smearing the operator with a different smearing function over the boundary of this wedge. So that's called AdS Rindler reconstruction. Now let me make two comments about that. What? It's kind of the topological hyperbolic black hole. So it's a zero temperature hyperbolic black hole. That's right. Okay. So let me make two comments about this. So the first is that we can have again the same discussion that we had there. So now, since we're looking at half of the boundary of the wedge looks something like that when we sort of project it onto the boundary cylinder. And again, by using the Heisenberg operator equations of motion in the boundary theory, I can now collapse all this to some horrible non-local operator, but now it's not so non-local. It's a horrible non-local operator with support only in a hemisphere of the boundary. Okay? So that's why it's called subregion duality. It's saying that there's a subregion of the bulk where the operators which are in that subregion you can represent in a subregion of the boundary. So that's one comment. Another comment is that by using the conformal symmetry, there's nothing special about the equator here. I can move this region around by acting with the conformal symmetry. So a similar story will be true, say for this region here, and also for this region here. So a little harder to draw, something like that. And in fact, so for any region on the boundary which is ball-shaped, so here, unfortunately, since I can only draw an AdS 3, this statements work for any interval. But in higher dimensions, the thing that's special about the boundary of the Rindler wedge is that this is a ball, like a round ball in the boundary metric. Here, just an interval, so that's a ball in one dimension. But a ball in higher dimensions is that's a subset of the connected regions. But for any ball-shaped region, I can do some conformal transformation to map it to the AdS Rindler wedge, and so it means that for any ball-shaped region, I can define this subregion in the bulk, which is just the image of the Rindler wedge under the conformal transformation, and then I can do exactly the same thing. So anything in this tiny little region here can be represented in this tiny little region in the boundary. Anything in this big region here can be represented in this big subregion in the boundary. Okay. And in fact, there's a sort of very obvious guess for what the statement should be for an arbitrary subregion in the boundary. So let R be a general spatial CFT region. Then we can define something which is called the causal wedge of R. So it's, well, I'll write the formula and then say what it is. Okay, so this is some sort of relativist mumbo jumbo. So let me say what the definitions are. So D of R means the boundary domain of dependence of the region. So here, this was a spatial subregion. Its domain of dependence is this causal diamond here. But we can define that for any region, not just a ball-shaped region. Okay. Then this J plus and J minus are in the bulk the causal future and past of that boundary domain of dependence. So if you look at these wedges here, right, it's kind of clear that's what's going on, right? Like I can take, so the future is like something like this, right? And the past is something like this. And then their intersection is this wedge. Okay. Now, why might that be a reasonable region to talk about? Well, there's kind of a parable I can tell you. So say I'm someone who can only access simple things in the boundary, and I want to know what's going on in the bulk. Well, for any point which is in this region, I can send a mission to find out. So because the point is in the future of the domain of dependence, I can send in a little rocket ship here to get to the point, okay? And then since it's also in the past of the domain of dependence, then the rocket ship can take a sample, and then it can fly back to the boundary and tell me what it found, okay? So of course, really you have to make some statement about solutions of PDEs and so on, but at least this suggests that it's plausible that this procedure of sort of solving the bulk equations should be able to generate some formula like this for a point in the causal wedge of an arbitrary region. Now let me emphasize that's a conjecture about PDEs. It's hard actually, I think, to show that because, well, I'm not a PDE person, so I never remember what's elliptic and hyperbolic, what's hyperbolic. But whichever one is good for the initial value problem, this is the other one. Because you're going sideways, right? Like so good evolution is like this, and you're going this way. And so that makes the PDE problem delicate. And somehow in the cases with symmetry, you sort of know it's going to work. We can just work it all out. But this k hat that we get, well, I was sneaky and I didn't tell you what it is, but it's actually a very subtle object. It's not really a function, it's a distribution. And so you're only allowed to, basically it kind of only makes sense if the thing you integrate it against is something that's actually an operator in the CFT. It doesn't make sense being integrated against an arbitrary function. Yes?
Now I want to go back to my question of how are you solving these equations, which boundary conditions are you putting in on the boundary of this?
Yeah. So, so
Coming from the past,
so-
you go into the future.
yeah. So here it was kind of clear. Well, the only thing I had to do was I used that the phi obeyed this r to the delta kind of boundary conditions at infinity.
Boundaries of these horizons of this region.
Here, yeah. So here it turned out I didn't have to assume anything about that, and I got a unique answer. Yeah, because somehow, right, so this is one of those subtle things. So because whatever you throw here, it ends up having a tail out here, which is good enough. What? No, I'm only considering normalizable modes. So non-normalizable modes do not exist for me, okay? But even the normalizable one, so it has a tail which is smaller, but it's still enough. Yeah, I mean, this whole all these modes are normalizable, and I'm picking up the tail of the normalizable mode out here and using that. Okay, and so the subtlety has to do with the fact that in some appropriate sense that tail is exponentially small, and so then you can worry about whether the dependence on the initial conditions is continuous or not, and that's what's associated to the distribution. But for any PDE, there will be this tail, and so you can try to use it. Yeah?
Can you label C of R and D of R on this?
What?
Can you label C and D of R?
Oh yeah, okay, so D of R is this thing here on the boundary. Here, it's going to be complicated if I try and do it here, but this diamond kind of wraps around on the cylinder here. Okay, and then the C of R is like this wedge of cheese in the bulk. Yeah. So I don't know, this whole thing is C of R. I don't want to write it because it'll make it messier, but yeah. Yeah, there are nicer figures in the notes than what I can draw on the board. So, So in general, this hard PDE problem has not been solved for arbitrary regions, and I'm not going to solve it for you today. It would require someone who understands distributions on curved space. Okay, and that's a very subtle thing. It's actually an analysis. It's something that people only started understanding in the 90s. It's called micro-local analysis. And so you really need to be a professional, and I'm not a professional, so I can only do the case with symmetry. But it actually doesn't matter, because I'm going to later in the lecture, well, not this lecture, but later in the lecture series, give you a different reconstruction method, which is not based on solving the bulk equations of motion, which I will argue allows you to get everything in a region which is actually larger than the C of R. And since it's larger than the C of R, in particular, it works for the C of R. And so at least formally, there is a proof that you can do it in C of R, but in general, not necessarily using this equation of motion solving technique. That's the PDE thing, is to show that just solving the equation of motion is enough for C of R. Okay. Now, let's take a timeout and take stock. So far what we've been doing is really pretty dumb, right? We're just solving the bulk equations of motion. If that was all there was to holography, that would be kind of sad, right? I mean, it would mean holography was really kind of a trivial thing. Like if that was quantum gravity, I don't know, we should all go work at Google or something, right? I mean, and maybe here's another way of seeing that, right? So say in the bulk now, instead of doing gravity, we're just doing quantum field theory. Let's do lambda phi to the 4 theory in the bulk. Everything I said here we can do, right? We can solve the equations of motion, and in lambda phi to the 4 theory, we can get some equation like this that tells you that phi sitting here is related to some integral of some object limiting value of phi over the boundary. Okay, so, but the thing is, it won't actually be a CFT, right? For example, in phi to the 4th, one obvious thing is there won't be an energy momentum tensor, because if you're just doing phi to the 4 theory, there's no graviton, right? More generally, right, the sort of objects that you construct by extrapolating the things to the boundary won't obey the axioms of CFT if you just start with some some quantum field theory in the bulk. So the really interesting thing about holography, which I have not captured in this discussion, is the interplay of locality in the bulk with locality in the boundary, right? Somehow, you know, the complicated thing is to show that all this machinery is consistent with locality in the boundary CFT. So let me first start by sort of attempting to convince you that it's not, and then we'll sort of see what we have to do to fix things. Let's see how I'm doing here. Okay. Am I going to 110? Is that the idea? You're the chair? I'm going to 110. Yeah. But we started 5 or 10 minutes late, so I just want to know if that 5-10 minutes is subtracted from me or not.
4 minutes late, and that.
Okay, 4 minutes later. Okay, very good. All right, very good. Okay, so good. So now let's try to see why what we just did was a little bit too naive. So let's consider a time slice of the bulk, and let's consider an operator phi of little x sitting in the center of the bulk. And also let's consider in this CFT some operator O of big X sitting out here. Locality in the bulk, so bulk locality, says that the commutator of phi of big X O of big X with phi of little x is 0 because they're space-like separated. Now this is one of those points where you might complain about the gravitational dressing, but if you do, I'll just tell you there's a version of what I'm about to say which still works, including the gravitational dressing. So let's just not worry about it. But this is a very puzzling equation if you think about it for too long. Because the boundary theory is supposed to be a CFT, or more generally a quantum field theory. And in a quantum field theory, or well, since Nadia's here, I have to be more precise. In a quantum field theory on a space which is topologically trivial, the local operators are all there is. We typically think that every operator in the Hilbert space, on the Hilbert space of a quantum field theory on a topologically trivial space, is just generated by the local operators. So the intuition for that, maybe think of it like a spin chain or something, right? You just say we just had a bunch of spins going around here, right? So then the Hilbert space is just a tensor product of what's going on in each of the spins. And then, for example, all the operators on the Hilbert spaces are sums of products of Pauli operators on the individual sites. But then what that means is if you have an operator that commutes with all of the local operators, it just means it commutes with all the operators. But if you commute with all the operators, you're the identity. And it's very boring to be the identity, right? I don't think I'm the identity. And so what this seems to say somehow is that this is kind of a no-go theorem for holography, right? It says that you can't commute, you can't have locality in the radial direction in a theory that's local on the boundary. And actually, were we trying to do quantum field theory in the bulk and not quantum gravity? That's a proof. Okay, that's a proof. So, which is good, right? Because quantum field theory should have the decency to know what number of dimensions they live in, right? And this is kind of expressing that fact. Okay. But somehow the fact that it's gravity must tell us that this equation isn't really true, or it's only true in some restricted setting, right? But it seems very true in this room, right? Like, I mean, we have gravity, but nonetheless, when they do the physics at the LHC, they see this equation, okay, to a very good approximation.
The same equation would be true if you just had a QFT in the bulk.
Yeah, that's what I'm saying, right? But if I had a QFT in the bulk, this equation would be true, and then we would conclude from that QFT in the bulk is not equal to QFT in the boundary, which is true. Yeah, the problem is that this crazy guy Maldacena told us that when it's gravity, it is equal to the quantum field theory in the bulk, in the boundary. What?
But he didn't say that 5 is. geometry object that shouldn't have existed.
Well, good. So it has, but again, in this room, it seems to exist to a pretty good approximation. So we have to understand why that is.
Equation is only showing some approximation.
Yeah, that's right. So that's what we're going to try to understand. Yeah, yeah. So somehow this is somehow wrong to ask for this, you know. But on the other hand, this is what we learn, you know, in quantum field theory class on day 1, or at least it's what you should learn in quantum field theory class on day 1. So then if we're going to start modifying this equation, we have to understand how the modifications are consistent with our experience of locality and causality on a day-to-day basis, despite the fact that there's gravity.
Actually, even for quantum field theory about, I don't know if people have studied very carefully the question of what exact objects we cannot extract from boundary S matrix, from the boundary S matrix. Because the boundary provides like the S matrix for the theory in the bulk.
Yeah, yeah, yeah.
And what exactly is there more in the theory in the bulk that is not the S matrix?
Well, I think but remember, this whole procedure I did, I could have done in quantum field theory. So I can take everything in the bulk and turn it into just sufficiently complicated boundary things.
If you're in the bulk,
Yeah, yeah.
then this machinery allows you to compute the S matrix from boundary excitations.
Yeah, 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 that's right. But the boundary excitations don't obey the axioms of quantum field theory all by themselves. No, 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 no.
I mean, there's no energy momentum tensor, but they commute outside of the light point.
No, yeah, that's true, but that's not all the axioms. Yeah, that's right.
But they obey this equation.
Yeah, yeah, but what they don't obey is the equation that all the operators are just made out of these, and so, that these generate the entire operator algebra. Yeah. Okay. Good.
But what happens if you're very close to the boundary?
What?
What happens if you're very close to the boundary? It's fine.
Well, it's still true as long as they're space-like separated, right? Yeah. So this is a Cauchy slice. So any 2 points that are not equal on this slice are space-like separated, so they commute. Okay, so let me try to formalize this intuition a little bit that you're not allowed to commute with all the local operators and be non-trivial in quantum field theory. So that's actually, so I didn't make that up. That's something which is called TSA. So it's not whatever Transportation Security Administration. That's for the Americans. No, it's the time slice axiom, and it's something that you can read about in Streeter and Whiteman or Hogg, which these kind of books that I'm embarrassed to have read, but. Actually, probably you should all at least look at them. So what the time slice axiom says is that in any quantum field theory, if you have if you're being rigorous about quantum field theory, then the local operators don't really exist. So you have to smear them against test functions f of x. And then what the time slice axiom says is that if you consider a neighborhood of a Cauchy slice in quantum field theory, if you have a bounded operator that commutes with all the smeared local operators that are smeared within this open set, then that operator has to be proportional to the identity. Okay, so that's the...
Shor lemma.
Yeah, it's kind of the continuum version of Shor's lemma. That's right. Yeah. Yeah, it kind of says that these guys act irreducibly on the Hilbert space. Okay. So anyway, so somehow holography has to solve this problem. Okay. So that's the lesson of this. In fact, I can use this Rindler reconstruction that we were just talking about to make this seem even more sort of surprising. So now let's look at this slice from above, and here's phi of x. Okay, now say over here O of x is your favorite local operator. Right over here. Just somehow you picked your favorite local operator on this time slice. Well, by using the Rindler reconstruction, I can pick a subregion which is like that, so that this phi of x is in the wedge of that subregion. And then I can represent it in the CFT like this. Okay? But now once I've done that, this is really true. Because now we're in the CFT, and I have an operator with support here and an operator with support here, and now the commutator really is 0. It's not 0 plus something, it's 0. Okay. But then you could say, okay, fine, maybe that was your favorite local operator, but actually no, you change your mind, now your favorite local operator is over here. Here's phi of x. Well, that's okay. I can now do the Rindler reconstruction this way. And again, I get some CFT representation of phi where this commutator is literally 0. And clearly I can do that for whichever one you pick. Okay. And now you can't rely on small errors in this equation to save you. Of course, then the question is the Rindler reconstruction that I did this way really the same operator? as the one that I did this way. Right? If they are, then you're dead. Then you've really in contradiction with the locality of the boundary CFT. So somehow they have to not be equal to each other. Okay. But again, now we have to understand that, because from the bulk point of view, they were just Bogolubov transformations. So from the point of view of solving the scalar equation in the bulk, they're exactly the same operator. Okay. So again, somehow we have to make sense of that. And so my favorite, so okay, and then it's always the same puzzle, but let me express it one more way, just to kind of, it's good to have different ways of thinking about things. Also, this one I guess I'm contractually obliged to draw. So say now we've got phi of x sitting here in the center of the bulk, and now let's divide the boundary into three regions, A, B, and C. Well, so I can draw these. So I can draw these Rindler wedges. So for A, it looks like this. For B, it looks like this, and for C, it looks like that. And so you can see this phi of x is not in the wedge of any one of these regions. So there is not a phi A, a phi B, or a phi C. But somewhat bizarrely, it is in the wedge of the union of any two of them. So if I consider A and B together, then now the edge of the wedge is over here, and so this phi of x is in the wedge. Okay? So there does exist phi AB, phi BC, and phi AC. And again, this is kind of weird, right? Because, again, in quantum field theory, right, operators somehow they should have the decency of knowing what their spatial support is. And here we're saying we have an operator which is definitely not supported in A or in B or in C. It sounds like it's nowhere, but actually no, it's in A, B, and BC and AC. So yeah, somehow, so from the bulk again, it's just obvious that these statements are true, but from the point of view of the boundary locality, it's quite surprising, or at least it was to me at some point. Okay, so this is all, again, these are just various, all this stuff, you can just kind of view it as sort of being a little bit more formal about the fact that holography is surprising. Somehow there's this funny radial, how can you be local in this extra radial direction, Okay, so now my goal for the rest of this lecture and the next one is to convince you that once you decide that you should think about the correspondence as a quantum error correcting code, then this is not so mysterious. But since I know that there's some emotional baggage in having to understand what new words mean, let me just say a little bit about the punchline now from the bulk point of view, okay, so that we all have some sense of where we're going. So the key thing you have to realize, which has already been suggested by several members of the audience, is that demanding this as an operator equation is kind of absurd. Because this phi doesn't really make sense in most of the states of the CFT, right? So let's ask. So what is any students want to say what a typical state in the CFT looks like from the bulk point of view? Yeah, right. But not just any black hole, right? So a typical state in the Hilbert space of quantum field theory is a state of very high energy. And so a typical state is actually one where not only is there a black hole, it's a black hole that's sort of eaten all of the bulk and there's nothing left. Okay. So in such a state, why should we expect that something like this makes any sense at all? So somehow what we really need to do is we need to learn how to talk about situations where we want these things to be true only in some of the states, sort of the states where it's reasonable to ask for these things to be true. And so what quantum error correction really is it's kind of a systematic way of doing that. It's a way of talking about how you can have sort of a subspace of the Hilbert space where you have some algebra which is realized naturally on that subspace, and then understanding how that algebra fits into a larger Hilbert space which is local with respect to somehow some other degrees of freedom that aren't so obvious from the point of view of the bulk. Okay. So we can say all that without talking about quantum error correction, but hopefully I'll convince you that somehow quantum error correction is just so good at this that it's kind of crazy not to think about it that way. Okay. Let's see. Okay. So that's all I was going to say about AdS CFT for a while. Now we're going to take a detour and we're going to learn about quantum error correction. So any other questions about these things? Okay. All totally clear and transparent, I'm sure. Yeah.
So this is problem me before about the linear wedge reconstruction or entanglement wedge reconstruction.
Yeah.
If you take the whole boundary theory and split it up into infinitely many pieces,
Right, right.
then there's no bulk anyway. I mean, if you consider each of them individually, right?
Right, so that's kind of what I was saying in this picture with the 3 regions.
Yeah.
So you can take the limit of that and you get the statement that you said.
Yeah.
That's right, so we've got to figure that out.
The same concept exists in the matrix model. Couldn't you?
I would love to understand if some version like this exists in BFSS. I guess,
Kind of diagonal.
yeah, it's kind of,
Operator, it's
how do we think about subsystems of degrees of freedom in the matrix, right? Because,
just a smaller.
yeah, but that's not gauge invariant, right? Because there are gauge transformations that,
It's also
no, this is gauge invariant. I'm just taking subregions of the boundary, right? So that's a gauge invariant thing.
oh, I thought it was meant not gauge invariant.
No, from the matrix, yeah, from the boundary point of view. Yeah, yeah. No, yeah, I agree that there should be something like that, and I would love to understand it, but I don't. Yeah, that's one of the big things is to try to do this in flat space. Yeah, okay. All right, so now let's talk about quantum error correction.
But
Oh.
something like the qualitative idea is that it would be almost like a unit matrix in a relatively small block, but away from that it would be a horrible.
That's right. Yeah. Somehow there's got to be some way of extracting kind of the subset of the matrix, which is just small perturbations. Yeah, gravitons and so on. Yeah. And I think it's actually high time to revisit that. Because BFSS sort of fell by the wayside after AdS CFT was invented, and it seems like of course it's harder to understand. I mean, I'm always I can't understand null quantization. That's for me is always kind of the starting point of my confusion with that. But yeah, I think it's probably time to revisit it. Okay. Anyways. Okay. So now quantum error correction. So what is this quantum error correction business? So the idea of any error correcting code, quantum or classical, is that I want to send you a message, but I'm sending it through some system which is imperfect. So for example, you could be the Voyager spacecraft, and I could be NASA, trying to communicate with you by sending you a message. But all kinds of things could happen to that message before it makes it all the way out to Voyager, right? And so somehow you want to have some way of reliably communicating with Voyager, despite the fact that your message, any particular message you send, could well be lost. Okay. So there's an obvious protocol for doing that, which is called the repetition code, which you all probably thought of as soon, or you will think of if you think about it for 10 seconds. So say I have a bit, 0 or 1, and I want to send it to Voyager. Well, the obvious thing to do is I don't just send the bit, I send 100 copies of the bit. I send it 100 times. And now say maybe each bit there's a 40% chance that it gets corrupted. It's okay because if I send it 100 times, probably 60 of them will all agree with each other and 40 of them won't, or maybe will be lost. And you can just do majority vote. And the more bits that I send this way, right? Although it's always 40% that are corrupted, kind of the error fraction gets smaller as I send more bits, basically by the central limit theorem. And so if I send enough, I can communicate very reliably, even if each particular bit I'm probably going to lose it. Not probably, but there's a 40% chance I lose it. In fact, any percentage less than 50 is fine. If there's a more than 50% chance that each bit is corrupted, you're screwed. There's a theorem about that. Okay. And in fact, if you think about it, that's kind of also what happens in the hard drive of your iPhone or whatever. You have the memory is like spin blocks, right? And so if you don't just have one spin, you have a bunch of spins, right? And that's kind of what makes it reliable against external perturbations. If one of them gets messed up, then all the other ones are still there. And there it's actually even better because then the magnetic field of the other ones kind of wants to flip the one that got mixed up back to where it belongs. So repetition code, that's it, right? No more enough with the error correction, right? Well, unfortunately, no, because the problem is that the repetition code doesn't work in quantum mechanics. So it's fine for classical coding, and in fact, if all you care about is protection and you're not worried about, I don't know, whether Putin can read your email or something, then you should just do the repetition code. But quantum mechanically, you can't because of the no cloning theorem. So the no cloning theorem says that there's no machine you can build where if I come to you with the quantum state and I come to the machine and I put it into the machine, then out come 100 copies of the quantum state. That's not how quantum mechanics works. Right? So like very naively, you could imagine a machine where I send in a qubit in the state I, and then I send in some extra qubits, which I start out 0. Well, I could certainly have a unitary transformation which sends that to I. That's fine, right? I mean, nothing wrong with that unitary transformation. But the problem is now if I try to act with this transformation on the sum, CI 0, 0, right? So that's kind of what I would want to do, right? Well, unfortunately, then I get this, which is definitely not 3 copies of the state that I wanted to send. Okay, and that's the basic problem with the no cloning theorem. So it can't you can't clone superpositions. So that sounds pretty bad, right? And actually, for a while, there was a period where people kind of thought, okay, maybe we're never going to have quantum computers because of this. Okay. But actually, it turns out that there is something that you can do. There's a different kind of redundancy, which is not quite this redundancy, which is able to protect quantum information against noise. And I'll tell you the slogan first, and then we'll do an example. So the slogan is that you want to store the information non-locally in the entanglement between many qubits. It sounds good, right? On the cloud, yeah, right. And you want to do machine learning to, yeah, you want to machine learn the entanglement between, the nanotechnology fabricated. Okay, anyways. Right. So, okay, so that sounds good, but okay, is it actually something you can do, or is it just some slogan like, some of these other things just mentioned? Well, it turns out that it is possible. And so, as with any new thing, I should just give you an example where we can all see that it works, rather than trying to give you some general proof that it's possible. So, the idea, the sort of the simplest code is called the 3-qubit code. There's only 2 annoying things about the 3-qubit code. The first is you have to know it is a qubit, which is like a qubit, except it has 3 states, so 0, 1, and 2. So you can think about it like a spin 1 atom or something. Okay. The other tragedy of the 3-qubit code is that 3 qubits have 3 states, and there's also 3 qubits. So there's 2 3s that mean different things. So that's kind of the pedagogical tragedy of the 3-qubit code, but you're just going to have to live with it. So the idea of the 3-qubit code is that we have what's called a logical qubit that we want to encode into 3 physical qubits. Okay, so this logical and physical is like what we had in the repetition code. The logical information is the message you're actually trying to send. So say when I send you 100 bits, I'm sending you 1 logical bit, but I'm using 100 physical bits to do it. Okay, so that's the redundancy. And here there's also a redundancy because I'm using 3 qubits to send you a 1 qubit message. Okay, and I just have to show you how I can do that without running into trouble with the no cloning theorem. So how do I do it? Well, the idea is that there's I encode the qubit into a 3-dimensional subspace of the 27-dimensional Hilbert space of 3 qubits, and here's what the subspace is. So I have 0, 0, 0, plus 1, 1, 1, plus 2, 2, 2. That's called the GHZ state. The logical 1 is encoded 0, 1, 2, plus 1, 2, 0, plus 2, 0, 1. And the logical 2, since it's qubit, is 0, 2, 1, plus 1, 0, 2. Okay, what's the last one? Guesses? Anyone paying attention? 2, 1, 0, yeah. Okay. All right, so that's the encoding. Okay, here, by this subspace encodes 1 logical qubit into the Hilbert space of 3 physical qubits. If you like math, then you can write this more simply by saying that I tilde is encoded in a sum over k. K plus I, k plus 2I K, where the addition is done in mod 3 arithmetic. Okay, now let me just make two comments about this subspace. So the first is that it's symmetric under cyclic permutations of the physical Q-trits. And so that's useful because it means that we only have to, we can just, check things not as many times to see that they work. What? This is I tilde, yeah. Sorry, yeah, it's not bad handwriting again. I tilde, that's right. Yeah, so you can have fun checking that this is, that I did the math right. Okay, so the first comment is that this is symmetric under permutations of the Q-trits. The second comment is that all of these states are very entangled. So if you look at these states, none of them is even close to being a product state of any subset of the Q-trits. Okay. Now, the claim to fame to this code is that I can also write the encoded states. This is I tilde. As what I get by acting with a certain unitary transformation with support only on the first two of the Q-trits, acting on a state which is I on the first Q-trit, and then some fixed state chi on the second two, where this chi is just a maximally entangled state 0, 0 plus 1, 1 plus 2, 2. Okay. All right, so that's another homework problem is find the U. Find the U1, 2.
The sigma 3.
What?
Sigma 3 also.
This is the identity, sorry. This is the identity on the third Q-trit. Yeah, usually I don't write the identity, but Greg Moore gave me a long lecture about how it, you have to write the identity. I'm probably not going to write it after this, but I always write it once just so Greg will be happy. Right, because maps include their domain. Okay. Okay, so I claim that there is a U12, a unitary with support only on the first two Q-trits such that I can get this subspace like this. Okay, that's a homework problem for you to figure out what's the U12. Okay, why is that interesting? Well, so say I send you the state psi tilde, which I got by acting with U12, psi on the first Q-trit, chi on the second two. Okay. So in my lab, well, I don't have a lab, but in someone's lab, someone takes the state that I want to send and puts it on the first, spin 1 particle, and then runs it through their quantum computer to encode it into 3, and then sends you the 3 in the mail. Okay. But say that there's some tragedy and the third Q-trit gets lost in the mail. Budget cuts at the post office or whatever, the quantum post office. Well, who cares? Because you can take psi tilde. Well, you don't have psi tilde, but you've got the first two Q-trits in psi tilde. And you can take it down to the basement to your quantum computer, and you can act on it with U12 dagger. And you can do that because this only acts on the first two, so you don't need the third one. And then after you do that, hey, look, here's the state on the first Q-trit, which is in your lab, so you have it. And then you've got some noise in the second one because you don't have access to the third one, so you just have some random bit on the second one. And moreover, well, if this is true for 1 and 2, then remember we said there's cyclic permutation symmetry of the subspace, and it means there's also going to be a U13 and a U23. Okay? And what that means actually is that if any of the Q-trits is lost, either the first, the second, or the third, it's okay. You can still recover the state that I sent you with no violation of the no-cloning theorem. Okay, so that should already sound a little reminiscent of this thing I said about the 3 regions and the operator in the center that you can recover from any 2 of the boundary subregions, but not the third.
Ones that lost could be measured also by someone else.
Yeah, it doesn't matter. Yeah, they can be thrown in the trash, they can be measured, you can change them, whatever you want. You don't need them. As long as the person who only can do local unitaries on them, it doesn't matter. Yeah, if they can pollute 2 of them, then you're in trouble, but that's the same thing we said before. Yeah. Yes, you need to know. So yeah, that's right. So I have to, when I send them, I have to send them in envelopes with labels. So you know it's the third one that was lost. There are actually codes where you don't have to know, but they're a little more complicated. And actually for AdS CFT, you always know which boundary subregion you have. So this is sort of the right parallel. Yeah. Okay. So let me say one more thing about this code, and then tomorrow I'll explain how it's related to holography. So the other thing is, so far we've been discussing sending a logical state. There's also an idea of a logical operator. So a logical operator is an operator which, acting on these code states, acts with matrix elements of some operator. So it's just operators that act within the code subspace. And it's important also that the dagger acts with whatever, O star ij. So logical operators are operators that act within the code subspace. They're called logical operators because they're the kind of things that you would want to be doing with your quantum computer. You want to be doing operations within the protected subspace. Now, for a general subspace, if you want to implement some transformation on that subspace, this O tilde is going to need to have support on all of the physical Q-traits. Right? I mean, because there'll always be some, this is some three-dimensional subspace. We can always find some operator on the whole Hilbert space that does whatever we want on this subspace. But usually it'll be an operator that involves all of the physical Q-traits. So, but sometimes you get lucky. And actually here we do, and it's kind of obvious. So I can define an operator O12, where what I do is first I act with U12 dagger to decode the message. Then, while the message looks like this, I act with whatever operator I want on the first Q-trait, and then I re-encode. And you see this is all just 1 and 2, so it's an operation I can do just with the Q-traits that I have. So with my quantum computer, I can act just using the first 2 Q-traits. I can implement whatever logical transformation I want. And again, by the symmetry, there will also be a O13 and O23. So with access to any of the Q-traits, I can implement whatever logical operation that I want. Okay. So that's very similar to what happened in holography, but I guess since we're running out of time, I'll spend 5 minutes of the next lecture explaining in detail how we can view this as a model of holography. Okay. And so I think I'll stop here. Thanks.
Urgent questions?
I suppose that my question would be kind of at the beginning,
Yeah.
which is if you've got this diffeomorphism between CFT and
Isomorphism. Yes.
isomorph, excuse me.
Yeah.
Between that and the anti-de Sitter space.
Uh-huh.
Why not, since we don't know exactly what quantum gravity looks like, why not use the classical approach?
What do you mean classical approach?
In other words, why not just establish a isomorphism between?
Well, that isn't any, but that's not any fun. We already understood. The goal here is to learn about quantum gravity. So my attitude is that quantum field theory is a thing that we understand since the 70s. And, it's just, you have the correlation functions, the local operators, et cetera. So, but we're allowed to do arbitrary things with the quantum field theory, and now we want to see what can we learn about quantum gravity from that, which isn't something that we've understood already. Yeah. Now, of course, there's different levels of understanding, and there are many things in quantum field theory that we don't understand, but we understand it much better than we understand quantum gravity. Yeah.
Yeah, so there are no more questions, so thank you.
Somebody